So let's look at this quick example. You see, there are two questions you have to ask yourself every time you want to do a synthetic problem. First of all, you have to ask yourself, is there any change in the carbon skeleton? Right. In this case, we began with a total of 7 carbons, but in this case we now have a total of 9. You see, so that means 2 additional carbons have been added. That's basically what it means. And the next question is there any change in the identity or location of the functional group? In this case, you can see we begin with an alkyne, but we are ending up with 2 aldehydes. You see, so you can see that there's been a bond cleavage, and that sounds more like an ozonolysis. So, but first of all, we have to add the additional 2 carbons, and to do that, we just simply use a strong base like sodium amide, and then use an alkyl bromide to attach the 2 carbons, right? And then, since we are going to carry out an ozonolysis, we will need a double bond. So you can either do a Lindlas with hydrogenation, or you can do a dissolving metal reduction with sodium in ammonia, and then you get the corresponding alkane. Once you get the corresponding alkane, you can now do an ozonolysis where you just slice the bond. See, and how do you do an ozonolysis? You treat it first with ozone and then with dimethyl sulfide as the reducing agent. Now, some syntheses require a change in both the carbon skeleton and the functional group. You see? So you analyze the structures, like I said, look at the reactants and the products, assess how the functional groups have changed, and then you need to review the proposed step to make sure that the radioselectivity and stereoselectivity in each step lead to the desired product. When we're talking about radioselectivity, we mean Markovnikov's, anti-Markovnikov's. When we're talking about stereoselectivity, we mean whether it goes anti or syn, and those are the kinds of stereoselectivity we have looked at, right? And also we know whether it goes via inversion of configuration for an SN2 or via racemization for an SN1. Now, for the synthesis below, we want to analyze the structures of the reactants and the product. We have an alkyne, right? And here we have a dibromoalkane. You see. Now, what we observe, if we look at how many carbons we have here, we have a total of 7 carbons, right? Now, if you look here, we now have 8 carbons. What does that mean? You see, what does that mean? It means that first of all, we had to add 1 additional carbon. Already we know that if you make the alkylamide with a base, and then you do an SN2 substitution with methyl bromide, you are able to extend the chain by 1 carbon. And once you extend the chain by 1 carbon, you can now make the double bond. And from the double bond, you can now add bromine, which of course will proceed through something like this. So after what really happens is you are going to get, if I redraw it so that you can see what is happening, you see. So you have, this is what we had initially. It's going to be trans like this, you see. And so what's going to happen is the addition is going to be it's an anti-addition, you see. But upon rotation, if you rotate about this bond, you bring this bond down like that, you're going to get that. So it's actually, this is an anti-addition. It's an anti-addition, but upon bond rotation, the bromines look as if they are on the same side, but actually initially they were on opposite sides. It was actually an anti-addition. Now, for more challenging, complex, multi-step synthesis, it's often helpful to work backwards, and that we call that a read-through synthesis. Okay, although the same basic analysis is still performed. Okay, in the read-through synthesis analysis, you have to actually look at the final product and work backwards from there. For instance, look at this. You are trying to form a terminal alkyne, and at the same, and you are starting with a primary alcohol. You see? Now, if you look at this example here, you can see that the number of carbons does not change. See, the number of carbons does not change, because if you look at it, the longest chain, this is 1, 2, 3, 4. And there are 2 carbons there, so that's a total of 6. Here is 1, 2, 3, 4. That's 2 carbons. So the number of carbons does not change. Okay. The other thing we have to look, but the functional groups have changed. We have a primary alcohol here. This is a primary alcohol, and here we have a terminal alkyne. We have a terminal alkyne. So what's really going on here? So you have to analyze the reactants of the product, what forums we're dealing with, and then assess how the carbon scalency has changed. In this case, the carbon scalency is not changing, like I told you, and then you work backwards. You always focus on the last step. See, you focus on the last step, and the question is, how can I make a terminal alkyne? I can make a terminal alkyne from a dibromo compound, a vicinal dibromide. This is a vicinal dibromide. So we can make a terminal from a vicinal dibromide. And how do we make a vicinal dibromide? We can make a vicinal dibromide by addition of bromine molecule to a terminal alkene. See? And how do we make a terminal alkene? That means we can, if we had a leaving group, a leaving group like a tosylate here, in the presence of the base, we can make the terminal alkene. And how do you convert the OH to a tosyl group or tosylate, right? How do you convert it to a tosylate? You need tosyl chloride in presence of pyridine, and that's how you do. We learned how to do that last semester when we were looking at SN2 reactions. So if you have forgotten, please go and review it. Alright, so we already learned a method to synthesize alkyne. We know that from the dibromide, you can start from either a vicinal, you see, dibromide, or you can start from a geminal. You see, this is geminal dibromide. From a geminal or vicinal dibromide, you can make the terminal alkyne. Now, so you can make the terminal alkyne. Okay. Yeah. So the last step in this case must involve a geminal dihalide. Okay. See, this will still give you that. This will still give you that. All right. So, the synthetic arrow is used by chemists to show the sequence of reactions in the reverse direction. So this is a dibromide. Okay. This is a dibromide, and this dibromide, right, in other words, the alkyne can be made from the vicinal dibromide. Okay. So we know that. We're working backwards, and then we know that the alkene, actually the vicinal dibromide can be made from the alkene. Okay. And the alkene, like I told you earlier, you can make the alkene from an elimination of a terminal of a first degree alcohol. You can do that. Okay. So these are just some examples that we have looked at. You see, and I'm not going to talk more about this because I already reviewed it earlier. How do you convert an alkene to an alkyne? These are things we already talked about. So one step remains in the analysis, and that is how do you go? I mean, in other words, how do you make this? This can be made if you had did an elimination. This, see, an elimination with a base will give you that. And of course, you can easily convert this to a living group, a good living group, by using toxic chloride and pyridine. Okay. So if you review all the steps, the first thing you want to do is convert the OH to a good living group, and then you do an elimination to get the terminal alkene, addition of bromine to give you the vicinal dibromide, and then you do an elimination you get with sodium, an excess of sodium amide, and you get your terminal alkyne. Okay, so these are all the things that you need to know. Okay, now look at this example here. I think it was an example I shared with you earlier. See, it said perform a retrosynthesis. You see, again, you have only the addition of one carbon. See, only one carbon has been added. Okay, so we are working backwards. We always focus on the last step. In the last step here, you can see that this can be made from this. You see, and for this, that means this has to be an alkene. You need to have had an alkene prior. See, and the alkene must have been cis. It must have been a Z alkene. Okay, and then you can make, how do you make a Z alkene? How do you make a Z alkene? You can make a Z alkene, right, by addition of bromine and subsequent elimination with an excess of sodium amide. Right, you can make a Z alkene from an internal alkyne like this. Okay, the question is, how do you make the internal alkyne? The internal alkyne can be made from a terminal alkyne by simply extending the chain by one methyl group. You see, so that's basically how you do it. And if you look at all the steps here, which I've summarized for you, the first thing you want to do is extend the chain by one carbon. Once you have the chain extended by one carbon, then you want to do a Lindblad to give you the cis or the Z alkene. Then you do the addition of bromine, you get the anti-addition. You can see the bromines are anti with respect to one another. Okay. Alright, to build a molecule, you must choose the right tools for the job. So it is helpful to create a list of tools and categorize them into two sets. Tools that alter the carbon skeleton, that is, increase or decrease the number of carbons, and tools that alter the functional group. So you have to make this distinction. We already looked at one tool that will alter the carbon skeleton, and that's an alkylamide. We're going to look at other tools like the Gilman reagent, the Grignard, okay, later on in the semester. So you have to try to create your own problems. That's what I will share. Try to create your own problems, right, and swap them with your classmates and see how you can practice. The best way to do that is start with a relatively simple reactant compound. Choose the reagents to change the compound's carbon skeleton and functional group, and predict the structure of the product. Repeat a few more times. Then you take away all the intermediates and all the reagents, and you only show the reactant going to the product, right? And then you give it to your classmate and see if they're able to solve the problem. This is a very simple example, going from acetylene to propane. You see, again from acetylene to propane, you're adding one carbon. You see, that's basically what you're doing. See, and here you're going from, in this case 1, 2, 3, you're going from butane to cis-2-butene. You see, so you can do this. You can practice this on your own and get as much practice as possible. Okay, right? There's always more than one way of doing things. Okay, but chemists always find the more facile way. See, you can do, for instance, if you have a terminal alkene, you can go to the first degree alcohol using HBr addition benzoyl peroxide, or you can do a hydroboration oxidation. This will require a lot of practice, and that's what I want you to do.